It is 2:00 a.m. The pager is just absolutely screaming. You are staring at a Slack channel lighting up with furious messages from the customer support team. Your payment pods are throwing 502 bad gateway errors. Your worker nodes are crashing. And the CEO just joined the incident bridge.
Oh, the worst case scenario.
Right. If you have ever worked in modern cloud infrastructure, your heart rate just went up a little bit. Because when massive Kubernetes environments break, they do not break cleanly.
No, they really don't.
Yeah.
It is never just one thing.
Exactly. The diagnostic landscape is muddy, and a failure in your application is almost always a symptom of some completely invisible limit being hit, like 3 layers down in the network stack. So, welcome to this deep dive. Today, you are stepping into the crucible.
Yeah, we are looking at a leaked, incredibly comprehensive production interview guide. This is the exact kind of thing used to hire senior DevOps engineers at companies like IBM.
And it's brutal.
It really is. This isn't a vocabulary test. This is a 20-scenario gauntlet covering AWS Elastic Kubernetes Service, Helm architectures, deep stack network troubleshooting, and cluster disaster recovery.
Yeah.
I mean, it is explicitly designed to break candidates who only know the textbook answers.
And since we want to see how the pros actually keep these complex systems from collapsing under their own weight, we are going to run the gauntlet ourselves. I am taking the role of the grizzled principal engineer conducting this interview.
I love it.
I've seen every catastrophic failure mode a cluster can throw, and I do not accept surface-level YAML configurations as answers. I want the underlying Linux and network mechanics. You, my friend, are the candidate.
I'm ready.
Your job is to survive the 60-minute pressure cooker using real kubectl commands and battle-tested architecture logic.
Let's rack them up. I'll rely on the kind of hard-won knowledge you only get from actually trying to fix a melting cluster while half the company is literally watching you type.
All right, candidate. We are jumping straight into the deep end. The 2 a.m. firefighting scenario I mentioned earlier. Your pager fires. The critical payment processing pod in our EKS production cluster is in a CrashLoopBackOff state. Customers are actively getting HTTP 502 errors when trying to check out.
Okay.
I don't want a theory. I want your exact hands-on keyboard troubleshooting steps right now. Go.
Well, first thing I do is establish the blast radius. I mean, I am not making blind changes here. So I run a quick kubectl get pods -n payments -o wide.
Why the wide output?
Because I need to see if it's just one pod failing or the entire deployment, and critically, which specific physical EC2 node it is actually sitting on. Once I have the exact pod name, I need the forensics. So I run kubectl describe pod, and I just scroll straight past the configuration down to the events section at the very bottom.
The events section is a good start, but what exactly are you looking for? There is a lot of noise in Kubernetes events.
I am hunting for the container exit code. That single integer tells me whether this is an infrastructure failure or like an application failure. Specifically, I want to see if the exit code is 137 or 1.
Break down that distinction for me. Why do those specific numbers dictate our entire recovery path?
It all comes down to how the Linux kernel manages resources. Kubernetes is just an orchestrator. The actual work is done by the Linux kernel using C groups or control groups.
Right.
So I see exit code 137. That means the container was killed out of memory. What happens is the application tried to allocate more RAM than the Kubernetes limit allowed. The Linux kernel's own killer mechanism just stepped in, saw the process violating its C group boundary, and sent a sigkill signal.
Which is signal 9.
Exactly. In Linux, a sigkill is signal 9. Docker and container take the base fatal error code of 148, add 9, and give you 137. The operating system literally assassinated the container to protect the rest of the node.
The bouncer threw you out of the club.
Yeah, precisely.
But what if it's an exit code 1?
Exit code 1 means the container process tripped over its own feet. It is a general application error. Maybe a bad database connection string was pushed in a recent config update, or there's a fatal exception in the Java code.
How do you verify that?
To confirm an exit code 1, I immediately run kubectl logs on the pod name, but with the -- previous flag. That previous flag is absolutely vital.
Because the current pod is empty.
Yes. Since the pod is in a crash loop, the current container just booted up and has empty logs. I need the logs of the ghost container, the one that just died, to actually see the stack trace.
Okay, let's say you look at the events and it's the ohm killed scenario. Exit code 137. Every minute we are down, we lose $50,000. How do you stop the bleeding right now?
We need to loosen the kugroup boundaries immediately. I would bypass the CI/CD pipeline for a pure triage fix. I just run kubectl edit deployment payment -svc -n payments.
Live editing in production. Bold.
It's an emergency. This opens the live YAML in my terminal text editor. I scroll down to the resources limits memory block and bump it. If it was 512 MB, I double it to 1 GB. Saving and closing that file triggers the Kubernetes controller manager to immediately execute a rolling update, spinning up new pods with the expanded memory limit.
Okay, you've bought us some time by throwing memory at it, but you haven't answered the most important part of the scenario.
The 502s.
Yes. Why were customers seeing 502 bad gateway errors? Even if a pod crashes, Kubernetes is supposed to be highly available. Why was the load balancer routing live customer traffic to a pod that was actively choking to death?
Because the developers who wrote the deployment YAML lied to Kubernetes. They completely failed to configure a proper readiness probe.
Walk me through the mechanics of that failure.
By default, the kubelet agent on the node is quite naive. The millisecond the container process starts running, before the Java application is actually loaded into memory, before it has established its database connection pools, Kubernetes just assumes it is ready.
So it opens the floodgates.
Right. It instantly adds the pod's IP address to the active endpoints list, and traffic starts flowing. If you don't have a readiness probe checking a specific HTTP endpoint, like /health/ready, Kubernetes sends customer requests to an application that isn't listening yet. That results in a 502 from the Ingress controller.
And what about a liveness probe? Does that play a role here?
A liveness probe is the other half of the shield. A readiness probe dictates if traffic should be routed to the pod. A liveness probe dictates if the pod should be allowed to keep existing at all.
Meaning?
Well, if an application encounters a deadlock, like a thread gets stuck in an infinite loop, the process is technically still running. The kernel won't kill it, so it won't crash. But it cannot serve requests. Without an HTTP liveness probe constantly pinging the app to ensure it is actually responsive, Kubernetes will leave that zombie pod in the cluster forever, just eating traffic and dropping it on the floor.
Spot on. You stabilized the payments pod by fixing the resource limits and the probes, but while you were editing that deployment, your dashboard lights up red. 3 out of your 8 physical worker nodes just dropped into a not ready state.
Now that's bad.
Pods are getting evicted, and the cluster capacity is in free fall. What is your diagnostic approach?
When a node goes not ready, the Kubernetes control plane has lost contact with the kubelet running on that specific EC2 instance. So I start with kubectl describe node, and I look at the conditions array. I want to see if the kubelet managed to report a dying breath. Is memory pressure, disk pressure, or PID pressure flagged as true?
The conditions are all clean. It just says not ready. The API server has simply lost communication entirely.
Then the abstraction layer of kubectl is no longer useful to me. I have to drop down to the underlying operating system. I'd use AWS Systems Manager, or just SH, to drop directly into a shell on that failing EC2 instance.
And then what?
The first command I run is system_total status kubelet to see if the agent itself crashed, followed by journal_total-u kubelet-f to watch the real-time logs. Often you'll see disk space issues where the node is filled with abandoned container images.
True, but we are running an AWS EKS.
Yes. Since we are in EKS, there is a very specific silent killer that causes nodes to drop off the network entirely.
I was hoping you'd catch that. We are running T3.medium instances to save money on our worker nodes. Explain the AWS Elastic Network Interface Trap.
The ENI trap is one of the most brutal architectural bottlenecks in AWS. In Kubernetes, the networking model dictates that every single pod must have its own unique, fully routable IP address within your virtual private cloud, your VPC. To facilitate this, the AWS VPC CNI plugin attaches elastic network interfaces, which are essentially virtual network cards to your EC2 instances.
Right, and AWS strictly limits how many network cards a virtual machine can have.
Exactly. And they also limit how many IP addresses can be bound to each card. A T3.medium instance is a pretty small machine. AWS hard codes its limits. It can only attach a maximum of 3 ENIs, and each ENI can only hold 6 IP addresses. So 3 times 6 is 18. Subtract 1 IP for the node's own operating system, and you are left with exactly 17 usable IP addresses.
Meaning that node can physically only host 17 pods.
Total. And remember, every Kubernetes node runs mandatory system pods just to function kubeproxy osnode coordinates. That eats up 4 or 5 IPs immediately. So you actually only have room for maybe 12 of your actual application pods.
So what happens when pod number 13 tries to schedule?
If your cluster tries to schedule a 13th pod on that node, the VPC CNI plugin requests a new IP, the AWS API replies with a hard denial, the networking stack panics, and the kubelet crashes or becomes completely unresponsive. The node drops into a not ready state.
I have seen teams rip their hair out over this, buying massively expensive instances just to get a higher pod density. But since you identified the bottleneck, how do you resolve it immediately, and how do you fix it permanently without blowing up our AWS bill?
Immediate triage. I cordon the node using kubectl cordon. This puts a taint on the node so the scheduler won't even attempt to place new pods there. Then I drain it safely using kubectl drain with the ignore daemon sets and delete impeder data flags.
To get the healthy pods off.
Right. This forces the Kubernetes scheduler to gracefully evict the remaining healthy pods to other nodes in the cluster. Once the node is empty, I terminate the EC2 instance through the AWS console. The autoscaling group will detect the termination and spin up a fresh node to replace it.
And the permanent fix.
We enable VPC CNI prefix delegation. By default, the AWS networking plugin asks for IP addresses one by one. Prefix delegation changes the entire logic. Instead of requesting a single /32 IP address, we configure the CNI to request an entire /28 CIDR block, which is 16 IP addresses at once, and attach that entire block to the ENI. Yeah, suddenly that same cheap T3.medium instance goes from supporting 17 pods to supporting over 110 pods. It completely eliminates the IP exhaustion bottleneck with a single environment variable toggle.
Excellent. You survived phase 1. The underlying infrastructure is finally stable. But your development team, in an absolute panic over the earlier downtime, just hastily merged a pull request and pushed a buggy Helm chart update to production.
Of course they did.
It contains a broken database migration script. The app is failing. You jump into the terminal and run Helm Rollback My App 1, attempting to go back to the previous stable release. But your terminal spits out a fatal error. Release is in a failed state. It refuses to roll back. What do you do?
This is where understanding Helm's internal architecture is non-negotiable. Helm isn't magic. It doesn't have its own dedicated database running somewhere in the cluster to track deployments. Helm tracks the state of your releases by creating standard Kubernetes secrets directly in the namespace where the application lives.
So when a deployment fails mid-flight?
Exactly. When a deployment fails, maybe a pre-install hook times out, or the API server rejects a malformed YAML document, Helm panics. It writes a secret to the namespace, explicitly marking the current release version as failed. And Helm's default safety mechanism prevents it from performing any further operations, including rollbacks, on a release it considers corrupted or locked.
So how do you perform brain surgery on Helm to unlock it?
We have to manually manipulate Helm's memory. I use kubectl get secrets-n payments. I filter for secrets starting with johnhelm.release. I'm going to see a length of secrets representing the deployment history.
And you target the failed one.
Right. Let's say version 5 is the one that failed. The secret will be named something like helm.release.v1.myApp.v5. I forcefully delete that secret using kubectl delete secret.
By deleting the secret, you are literally erasing the failed deployment from Helm's memory.
Yes. As far as Helm is concerned, version 5 never happened. The highest known state is now version 4, which was successful. From there, I can cleanly execute the Helm rollback command or simply run a fresh Helm upgrade using the previous stable configuration.
But candidate, wait, you rolled back the Kubernetes manifests? What about that broken database migration the developers pushed? The one that dropped a crucial column in our PostgreSQL database. Did Helm roll that back?
No. And this is a catastrophic misconception I see a lot. Helm is a package manager for Kubernetes YAML. It manages deployments, services, and ingress objects. It has absolutely zero awareness of the internal state of your external databases.
So the table is still gone.
Yep. If a developer's init container runs in SQL script that drops a table, rolling back the Helm release only rolls back the application code that expects that table to be missing. It does not magically execute a reverse SQL migration.
So what is your playbook for the database?
The instant I identify a data tier corruption, Helm is irrelevant. I have to coordinate immediately with the database administrators. We either have to manually execute the reverse migration scripts provided by the developers, or if the data destruction is severe enough, perform a point-in-time recovery on the RDS instance to restore the database to the exact minute before the bad Helm deployment began.
Good. Infrastructure as code does not equal data as code. How do we prevent Helm from getting wedged in a failed state in the future?
2 things. First, we strictly enforce the use of the Helm diff plugin in our CI pipeline. It generates a Git-style diff of exactly what Kubernetes resources are going to change before the apply happens, catching glaring errors.
And the second thing?
Second, every production deployment must use the atomic flag. Helm upgrade -- atomic. If you use this flag, Helm treats the entire deployment as a single transaction. If any pod fails to reach a ready state within the timeout period, Helm autonomously rolls the entire release back to the previous successful state and cleans up after itself. No more failed state deadlocks.
You have recovered the app. Let's move to a network mystery. The pods are running, the database is restored, but suddenly Service A cannot talk to Service B. It is getting connection timeouts. However, Service A can talk to Service C perfectly fine, and Service C can talk to Service B.
Okay, weird routing issue.
They are all in the exact same production namespace. Walk me through your diagnostic funnel.
Well, if Service C can reach Service B, but Service A cannot, this is not a cluster-wide DNS outage or a systemic CNI failure. This is a targeted routing or isolation issue. I start at the service object layer. The Kubernetes service acts as an internal load balancer. It uses a label selector to find the pods it should route traffic to. I run kubectl get endpoint service B.
Why check the endpoints before checking the pods?
Because if the developer made a typo in the deployment, YAML will say they labeled the pods app will service beta, but the service object is looking for app equals service B. The pods will be running perfectly fine, but the service won't know they exist. The endpoints list will be completely empty. Any traffic hitting service B goes into a black hole.
You check the endpoints, the IPs are there, the service sees the pods. What is the next layer down the funnel?
Next, I need to isolate whether this is a DNS resolution failure or a raw TCP connection failure. I need to test this from the perspective of the failing pod.
How do you do that? The developers built these application containers using distroless images. For security reasons, there is no curl, no ping, no nslookup, and no shell installed in the container. You literally cannot kubectl exec into the pod and run network tools.
That's standard practice, and it's why I rely on ephemeral debug containers or a dedicated daemon set for troubleshooting. I would deploy a NetShoot pod.
NetShoot is great.
It really is. It's a specialized container image built specifically for network troubleshooting. It contains TCP dump, curl, nslookups, iperf, everything. Since I need to test from the perspective of Service A, I can use the kubectl debug command to attach a transient NetShoot container directly into the existing network namespace of the Service A pod.
I love kubectl debug. It's like plugging a diagnostic laptop directly into the server rack, so you're attached. What is the test?
First, nslookup service-b.cluster.local. I query the core DNS server.
Core DNS responds immediately with the correct cluster IP for Service B. DNS is completely healthy.
If DNS resolves, but the connection still times out, we're almost certainly dealing with an intentional firewall drop. In Kubernetes, that means a network policy. By default, Kubernetes namespaces have an open floor plan. Any pod can talk to any pod. But zero trust environments implement default denied network policies.
So what are you looking for?
I would immediately run kubectl get network policy-n production. I bet someone deployed a policy for Service B that explicitly allows ingress traffic from pods labeled Service C, but completely forgot to add the labels for Service A to the whitelist. The CNI plugin, using iptables or eBPF under the hood, is doing exactly what it was told, silently dropping Service A's packets at the kernel level.
Spot on. You edit the network policy, whitelist Service A, and the connection is established. Let's pivot to storage. While you were fixing the network, a junior admin was trying to clean up an old, unused deployment. They deleted a persistent volume claim, a PVC, hoping to delete the underlying EBS volume to save money. But the persistent volume, the PV object, has been stuck in a terminating state in the terminal for 3 hours. The AWS console shows the EBS volume is still actively attached to an EC2 instance. Resolve this storage trap.
This is the classic Kubernetes finalizer trap. It is a safety mechanism working exactly as intended but causing a massive headache.
Explain finalizers. Why does Kubernetes use them?
Think of a finalizer as a cryptographic lock on a database record inside, etc. When you tell Kubernetes to delete an object, the API server doesn't actually delete it immediately. It checks if there is a finalizer array attached to the object's metadata.
And if there is?
If there is, it simply updates a deletion timestamp field and waits. The object is put into a terminating state. It is the responsibility of some background controller, in this case, the AWS EBS CSI driver, to perform the actual physical cleanup, like detaching the drive in AWS. Once the driver finishes, it reports back to the API server and removes its specific finalizer from the list. Only when the list is completely empty will etc. actually purge the record.
So if the PV is stuck in terminating for 3 hours?
It means the AWS CSI driver is failing to detach the volume. the finalizer kubernetes.io/pv protection is still present. Usually this happens if the EC2 node the volume is attached to suffered a hard crash or a network partition, leaving the AWS API in a confused state where it thinks the drive is still in use by a running kernel.
How do you brutally resolve this? We need that volume gone.
I bypass the Kubernetes abstraction entirely. I take the volume ID from the TV description, and I go straight to the AWS CLI. I run ozec2 detach volume -- volume aid, and then force it. I forcefully rip the virtual hard drive away from the ghost instance.
AWS confirms the volume is detached and deleted, but the Kubernetes PV is still sitting there in the terminating state in your terminal.
Because the API server still had the finalizer on the record. Since I handle the physical cleanup manually, I need to tell Kubernetes to skip its own cleanup process. I use the patch command.
What's the exact syntax?
It's kubectl, patch PV, the PV name, -p, and then a JSON payload, setting metadata finalizers to null. By explicitly setting the finalizers array to null, the API server sees an empty list, realizes all prerequisites are met, and instantly deletes the object from etc. The PV vanishes.
That is a dangerous, powerful command. What is the risk there if you do that on a volume that has live data you actually want to keep?
Oh, it's huge. If the storage class for that volume had its reclaim policy set to delete, forcefully removing the finalizer might trigger a race condition where the cloud provider deletes the volume behind your back. Which brings up a critical architectural rule. Production storage classes must always be set to reclaim policy. Retain. Even if a claim is deleted, the physical disk and its data must remain orphaned in AWS until a human manually approves its destruction. Only dev and staging environments should use the delete policy.
Excellent governance rule. Let's talk about promises and zero downtime illusions. You promised the business that our microservices would have zero downtime deployments. You proved it by setting the deployment strategy to rolling update. You explicitly configured max unavailable to 0 and max surge to 1. You guaranteed that a new pod would be fully ready before an old pod was deleted.
Sounds perfect on paper.
But during the last deployment, our Datadog metrics caught a vicious 15-second window where customer request returned 503 service unavailable. The CIO wants an explanation. You configured the YAML perfectly. Why did we drop traffic?
Because declarative YAML parameters don't suspend the laws of distributed networking race conditions. The API server did exactly what I told it to do, but the network layer couldn't keep up.
Unpack that race condition for me. This is one of the most misunderstood mechanics in Kubernetes.
When Kubernetes decides it is time to terminate an old pod during a rolling update, it initiates a shutdown sequence. But it does two distinct things simultaneously across two completely different components.
What's the first thing?
It sends an API call to the kubelet on the node hosting the pod. The kubelet issues a SIG-termed signal to the container's main process. For most web frameworks like Node.js, Spring Boot, or Go, receiving a SIG term is a command to gracefully shut down.
So it stops taking traffic.
Right. The application instantly stops accepting any new incoming HTTP connections, finishes serving whatever it's currently processing, and then exits.
And what's the second thing Kubernetes does simultaneously?
It updates the endpoints API to remove the pod's IP address. This triggers the kubeproxy daemon running on every single node in the cluster. kubeproxy has to talk to the Linux kernel and rewrite the iptable's routing rules to ensure no more network packets are sent to that dying pod's IP.
So we have the application shutting its doors and the network updating its routing maps. Where is the race?
The race is that a local SIG term is almost instantaneous, but propagating iptable's updates across a 100-node cluster takes time. It might take 2, 3, or even 5 seconds for every single kubeproxy to rewrite the network rules.
So for a few seconds, the network routing tables are completely stale.
Exactly. The Ingress controller and the other pods are still looking at an old map. They route live customer traffic to the pod's IP address. But remember, the application received the SIG term instantly and shut its doors. The packet arrives at the pod, hits a closed port, and is instantly rejected. The customer gets a 503 connection refused.
It is like a restaurant. At exactly 10:00 p.m., the chef turns off the ovens and locks the kitchen. But the hostess at the front door hasn't updated her seating chart yet. At 10:01, she seats a family of 4, hands them menus, but there's physically no one in the back to cook the food.
That's a perfect analogy. The system is disjointed.
So architect, how do you fix the restaurant?
We have to force the chef to wait for the hostess. We introduce an artificial delay using a pre-stop hook in the pod lifecycle configuration. In the container spec, I add a lifecycle block with a pre-stop exec command, usually just a simple sleep 15.
You just tell the container to sleep for 15 seconds. How does that solve the network routing?
Because the pre-stop hook blocks the SIG term. When Kubernetes decides to kill the pod, it executes the pre-stop hook first. So the container simply sits there, fully operational, happily accepting and processing new customer requests for 15 seconds. Meanwhile, in the background, the second process is happening. Kube-proxy is updating the iptables across the cluster.
The hostess is updating her charts.
Yes. By the time the 15 seconds are up and the pre-stop hook finishes, the actual SIG term is finally delivered to the application. But by that point, the entire network has been updated. No more traffic is being routed to that pod anyway. The pod shuts down in total silence, and we achieve true zero downtime.
Brilliant breakdown of mechanics. But if you add a 15-second sleep, don't you have to adjust the overarching timeout for the pod shutdown?
Yes, you absolutely do. The default termination grace period seconds in Kubernetes is 30 seconds. If your sleep consumes 15 of those seconds, the application only has 15 seconds left to gracefully flush its database queues and shut down before the kernel issues a hard SIG kill, which is exit code 137 again. I would bump the grace period to 60 seconds to ensure the application has plenty of breathing room to finish its work.
We are cruising now, phase 4. Upgrades, scaling, and security. The cluster is stable, zero downtime is secured. But our EKS control plane is running version 1.27, and AWS is officially deprecating it. We have to upgrade the entire cluster to 1.28. We have 40 microservices relying on this infrastructure, handling thousands of requests a second. I want you to walk me through the execution plan for a major version upgrade. Do not skip steps.
A major Kubernetes upgrade is a high-wire act. You don't just click a button in the console. Phase 1 is strictly pre-flight checks. I do not touch the cluster infrastructure. Kubernetes is notorious for evolving its API and completely removing older API versions.
Like what?
Well, if we upgrade the control plane to 1.28 and our CI/CD pipeline is still trying to deploy Helm charts using an API version that was removed, like how the old autoscaling /v2 beta 2 was removed in favor of v2, our entire deployment pipeline will instantly break.
How do you verify 40 microservices across hundreds of YAML files aren't using deprecated APIs?
I use an open source tool called Pluto. I run it against our live cluster and our Git repositories. Pluto scans every object and alerts us to any API versions that are slated for removal in 1.28. We force the development teams to update their manifest before we proceed.
Pre-flight checks are green. What is phase 2?
Phase 2 is the control plane upgrade. In EKS, AWS manages the Etc database and the API servers. I trigger the upgrade via the AWS CLI or Terraform to target 1.28. This takes about 30 to 40 minutes as AWS rolls the master nodes behind the scenes.
Wait, if you upgrade the control plane to 1.28, what happens to all our worker nodes running our applications? They are still running the 1.27 kubelet. Does the cluster break?
No, and this is the genius of Kubernetes architecture. It officially supports an N-1 node skew policy. The control plane is designed to be backwards compatible with worker nodes that are one minor version behind. A 1.28 API server can perfectly communicate with and manage 1.27 worker nodes. The applications running on those nodes experience zero disruption while the master nodes are swapped out.
The control plane is upgraded. Do we trigger the node updates now?
Not yet. Phase 3 is the most commonly forgotten step. Upgrading the critical add-ons. Before you touch the EC2 instances, you must upgrade Core DNS, the Kube-proxy daemon sets, and the AWS VPC CNI plugin to their 1.28 compatible versions.
Why is that critical?
Because if your networking plugin doesn't understand the new API server, when you try to boot up new nodes, they won't be able to establish a network overlay, and they will fail to join the cluster entirely.
Add-ons are updated. Phase 4.
Phase 4 is the node group rolling update. Using Terraform or the AWS console, I update the managed node group to version 1.28. AWS handles the orchestration. It provisions a batch of fresh 1.28 EC2 instances, waits for them to join the cluster, and then systematically cordons and drains the old 1.27 nodes. Because we already configured our pre-stop hooks for zero downtime, and because we have pod disruption budgets ensuring a minimum number of replicas are always available, the pods seamlessly migrate to the new nodes while serving live traffic.
Flawless execution. The upgrade is successful. But almost immediately after the upgrade, a massive marketing campaign drops. Traffic spikes by 400%. The CPU on our main application hits 95%. It is choking. Yet your horizontal pod autoscaler, the HPA, is sitting there doing absolutely nothing. It is not creating new pods to handle the load. The app is melting down. Why is your autoscaler asleep at the wheel?
The HPA is an API resource. It doesn't actually measure CPU itself. It relies entirely on an intermediary component called the metric server to gather the resource utilization from the advisor running inside the kubelet on every node.
Okay, so how do you check it?
My first step is to verify the telemetry pipeline. I run kubectl top pods. If that command throws a timeout or error, it means the metric server crashed during the upgrade and the HPA is flying blind.
I run kubectl top pods right now. It returns the exact CPU and memory usage of every pod perfectly. The telemetry pipeline is healthy. The metric server is working. I'm looking at the HPA object using kubectl describe HPA. What is the most common, brutal human error that causes this exact failure?
I guarantee the describe output says something like unable to get metrics for resource CPU, and the current CPU percentage reads as unknown. This happens because a developer forgot to define CPU requests in the deployment YAML.
Walk me through the math of why a missing YAML line breaks the entire autoscaling engine.
The horizontal pod autoscaler operates on relative percentages, not absolute values. If you configure the HPA to scale up when CPU hits 70%, you are asking Kubernetes to perform an algebra equation. But 70% of what?
I see.
Yeah, the baseline for that percentage is the pod's CPU request, the minimum amount of CPU the pod asks the kernel to guarantee it. If you define a request of 100 millicores, the HPA knows to scale up when usage hits 70 millicores. But if a developer deletes the CPU request from the YAML to get the pod to schedule faster, the HPA loses its denominator. It tries to calculate 70% of undefined.
And so it just breaks.
Completely. Because it cannot compute the math, the controller silently fails, aborts the scaling calculation, and does nothing, even as the node CPU hits 100% and the application dies. No requests equals no math. No math equals no autoscaling.
That is a brutal hidden trap. 2 missing lines of YAML and the whole automated defense mechanism collapses. You enforce CPU requests on all deployments via policy, and the scaling works.
And while we were enforcing policies, I would enforce a rule that we don't scale on CPU alone. CPU is a lagging indicator. By the time your application's CPU hits 90%, it is already struggling to process requests, and your latency has spiked. Auto-scaling takes a minute or two to spin up new pods. You are always behind the curve.
So what metric do you use?
For production, the HPA should be configured to scale based on custom metrics specifically, requests per second coming directly from the Ingress controller. You want to scale up the moment the wave of traffic hits the front door, not 5 minutes later when the servers are already drowning.
Fantastic architectural insight. Let's move to question 9. With scaling comes severe scrutiny. The CISO and the security team just audited our EKS environment. They looked at how we handle database credentials. They realized our passwords are stored in standard Kubernetes secret objects. They are absolutely furious, claiming we are running a completely unencrypted cluster. Your defense is required. Redesign this immediately.
The security team is entirely correct to be mad. This is the biggest open secret in Kubernetes.
Yeah.
A native Kubernetes secret is not encrypted. It is merely base 64 encoded.
Which is basically plain text.
Exactly. Base 64 is an encoding scheme used to safely transport binary data across text-based protocols. It provides zero cryptographic security. Anyone with permission to run kubectl get secret-YAML can copy the string, run it through a terminal decoder, and have the plain text production database password in 3 seconds. We need a zero-trust layered cryptographic defense. I will build it in 4 layers.
Impress the CISO. Walk me through the layers.
Layer 1 is securing the brain of the cluster, etc. All Kubernetes configurations, including those base 64 secrets, are stored in the etc. database on the master nodes. By default, that database is written to the underlying AWS EBS volumes in plain text. I would implement envelope encryption for it, etc.
Explain envelope encryption. It sounds complicated.
Think of envelope encryption like a bank vault. Instead of just locking the password in a box, you encrypt the password with a data encryption key. Then you put that key inside a hardened lockbox, a key encryption key, which is managed externally by AWS Key Management Service, or KMS. We configure EKS to integrate with AWS KMS.
So what happens if someone steals the physical drive?
Now, every secret written to etc. is cryptographically locked. Even if a rogue AWS admin managed to steal the physical hard drives running the master nodes, the data is completely useless gibberish without making an authenticated API call to AWS KMS to decrypt the master key.
That secures the data at rest. But developers still have to initially put those passwords into the cluster. If a developer pastes a production password into a YAML file and commits it to GitHub, your KMS encryption doesn't matter. The secret is compromised at the source.
Which brings us to layer 2. We completely eradicate native Kubernetes secrets as our source of truth. Developers will never type a password into a YAML file again. We migrate all credentials to a centralized audited vault, like AWS Secrets Manager or HashiCorp Vault. Then I deploy the external secrets operator into the EKS cluster.
How does that operator work?
The operator acts as a secure bridge. Developers commit a manifest called an external secret to Git. This manifest doesn't contain a password. It just contains a reference saying, I need the database password located in AWS Secrets Manager path/prod/db. The operator authenticates to AWS, securely fetches the real password over an encrypted TLS connection, and injects it directly into the pod's memory at runtime.
But wait, if the operator pod is reaching out to AWS Secrets Manager, how does the pod authenticate to AWS? Doesn't it need an AWS access key? If you give the pod an access key, haven't you just created a new secret that needs to be managed? It's a chicken and egg problem.
Not in EKS. This is Layer 3, the most powerful security feature in AWS Kubernetes. IAM roles for service accounts, or IRSA. We do not use hard-coded access keys. IRSA leverages OpenID Connect Federation. We tie a Kubernetes service account directly to an AWS IAM role.
Oh, nice.
Yeah, when the pod starts, the kubelet automatically mounts a temporary, cryptographically signed web identity token into the pod's file system. The AWS SDK inside the pod uses that token to assume the IAM role dynamically.
So the pod inherently possesses the AWS identity without any hard-coded credentials existing anywhere in the system.
Exactly. And we apply the principle of least privilege. The payment pod's IAM role only has permission to read the specific /prod/paymentsDB secret and nothing else.
And the final layer.
Layer 4 is strict Kubernetes RBAC, role-based access control. I write a cluster role that explicitly denies all developers and junior admins the ability to get, list, or watch secrets. Even if they have access to the namespace to view logs, the API server will reject any attempt to view the secret objects.
You've locked it down like Fort Knox.
Yeah.
Envelope encryption at rest, centralized secrets, identity federation, and strict RBAC. The CISO approves. But our users are less happy. This brings us to phase 5, timeouts and resource starvation. Our customer success team just opened a P1 ticket. Users are seeing intermittent 504 gateway timeouts when hitting the AWS application load balancer. The pods are perfectly healthy. Memory is fine. CPU is low. The network policies are correct. What is happening?
A 504 gateway timeout from a load balancer is incredibly specific. It means the ALB successfully established a connection, routed the HTTP request to our application pod, and then sat there waiting for a response and waiting until its internal stopwatch ran out, at which point it gave up and returned to 504 to the user. But if the pods are healthy and not overloaded, the application isn't actually taking that long to process the request. We've a race condition between idle timeouts.
Where do you look first to untangle a timeout race condition?
We have to look at the TCP connection lifecycle across 2 different layers. Layer 1 is the AWS ALB itself. By default, AWS configures the ALB with an idle timeout of exactly 60 seconds. This means if a TCP connection between the load balancer and the pod sits completely quiet for 60 seconds with no data flowing, the ALB assumes the connection is dead and silently prepares to drop it.
And layer 2?
Layer 2 is the backend application, say, our Node.js server and its own internal keep alive timeout setting.
I see where this is going. What happens if the Node.js developer wanted to be aggressive about saving memory and set the application's keep alive timeout to 60 seconds as well?
Then you get a collision. Let's say a connection sits idle. At exactly the 60,000 second mark, the Node.js application decides the connection is stale and quietly hangs up the phone. It sends a TCP FIN packet to close the socket. But at that exact same millisecond, a new customer clicks checkout. The ALB, which also waited exactly 60 seconds, thinks the connection is still barely open. It fires the new customer request down that exact same TCP pipe.
The ALB sends the request into a connection the backend just closed.
Yes. The packet hits a closed socket on the pod ignores it or resets it. The ALB is now waiting for a response to a request it sent down a dead pipe. It waits, receives nothing, and eventually throws the 504 gateway timeout.
That is maddening to debug because the logs show nothing. The application never even saw the request. What is the golden rule of thumb to fix this?
The downstream application's keep alive timeout must always be strictly higher than the upstream load balancer's idle timeout. If the AWS ALB is set to 60 seconds, you must configure your Node.js or Spring Boot server to keep connections open for 65 or 70 seconds. The load balancer must always be the entity that dictates when a connection is closed and cleaned up, never the backend pod.
That's a great rule.
And while I'm in the ALB configuration, I would also drop the target group deregistration delay the time the ALB waits before draining a target from the default 300 seconds down to 30 seconds. That massively speeds up our rolling deployments.
Consider the timeouts fixed. But while we were distracted debugging the load balancer, disaster struck. A junior developer thought they were authenticated to the staging cluster. They were actually authenticated to production. They ran kubectl delete deployment payments and completely vaporized a live revenue-generating service. We talked about RBAC earlier for secrets, but take me through the governance setup to prevent this catastrophic human error from ever happening again.
The read failure here isn't the developer making a mistake. It's the platform architecture, giving a developer the authorization to execute a destructive delete API call in a production namespace. We must implement absolute environment separation using Kubernetes RBAC tied to AWS SSO.
Walk me through the actual mapping. How do you tie a corporate identity to a Kubernetes permission?
First, we use AWS EKS access entries. We map the developer's corporate IAM role, let's call it AWS Dev Team, to a generic Kubernetes group name, like Dev Group. The magic happens inside the cluster. I create two separate Kubernetes role objects. Note that these are namespace scoped roles, not cluster roles.
Explain the difference.
A cluster role applies globally to the entire cluster. A role is fenced entirely within a specific namespace. For the staging namespace, I create a role that grants wildcard permissions, verbs.star, resources.star. I use a role binding to attach that role to the dev group. They have God mode in staging. They can deploy, delete, and break things all they want to learn.
And for production?
For the production namespace, I create a strict read-only role. The YAML explicitly defines the verbs, get, list, and watch. And it explicitly limits the resources, pods, deployments, services, logs. I bind that role to the same dev group.
So what happens when they run the delete command?
Now, when the developer authenticates, if they try to run kubectl delete deployment and staging, the API server allows it. If they run the exact same command in production, the API server intercepts the request, checks the RBAC matrix, finds no delete verb authorized, and immediately rejects it with a 403 forbidden error. They can look at production logs to debug, but they cannot touch the infrastructure.
Perfect governance. And how do we prove who did it next time? We need a paper trail for the auditors.
We enable Kubernetes API server audit logging. By default, EKS doesn't log every API call because it generates a massive amount of data. I run an AWS CLI command to update the cluster configuration, turning on audit logs and routing them directly to AWS CloudWatch. Every single API requests the user's identity, the IP address, the timestamp, the verb, and the target resource is permanently recorded and searchable. If someone tries to delete a deployment, successful or not, we have the forensic receipt.
The developers are securely locked out of prod, but now they are submitting tickets complaining about the staging environment. They are trying to deploy their microservices, but half of their pods are stuck in a pending state. They say, the staging cluster has 8 EC2 nodes. Our Datadog dashboard shows the overall physical CPU utilization is only at 40%. The cluster is mostly empty. Why is the Kubernetes scheduler refusing to start our pods? Candidate, explain this discrepancy to the frustrated dev team.
This is perhaps the most common fundamental misunderstanding of how the Kubernetes kube scheduler operates. Developers look at actual hardware utilization. Kubernetes schedule is based purely on allocatable reservations.
Give me a metaphor to explain this to a frustrated team.
Let's imagine the Kubernetes cluster is a hotel, and CPU cores are the beds. The hotel has 100 beds total. Currently, it's the middle of the day, and only 40 people are actually physically asleep in those beds. That's your 40% actual CPU utilization. It looks empty.
Right.
But 90 of the beds have been booked, paid for, and reserved by guests who haven't arrived yet. If a new person walks into the lobby and asks for a room, the hotel manager looks at the reservation book, sees 90% occupancy, and says, "Sorry, we are fully booked." The manager cannot give away a bed that is already reserved, even if it's currently empty.
So how does that translate to the cluster? What is the reservation?
The reservation is the resources requests block in the deployment YAML. When a developer asks for compu, which is one full core, as a request, they are guaranteeing that pod will have access to a full core if it ever needs it. The kube scheduler subtracts that one core from the node's total allocatable pool.
So they're hoarding resources.
Exactly. If a development team wildly over-provisions their apps requesting 2 cores per pod just to be safe, but the app is just a lightweight Python script using 0.1 cores, they are reserving massive blocks of empty hotel rooms. The nodes become overcommitted on paper. The scheduler does the math, sees that 90% of the CPU is requested, and rightfully refuses to schedule any more pods, leaving them in a pending state to protect the guarantees it already made.
So the fix is to right-size the requests using historical usage data from the metrics server. But what if the resources are perfectly tuned, the cluster has plenty of room, but a specific pod is still stuck in pending? What is the secondary cause?
That points directly to scheduling constraints, specifically pod anti-affinity rules. A senior engineer might have added an anti-affinity rule to ensure high availability. The rule might say topology key, kubernetes.io/hostname, with the required during scheduling, ignored during execution directive.
Translate that into English.
It translates to a hard rule. Never, under any circumstances, run 2 copies of this pod on the same physical server. If you have a cluster with exactly 8 physical EC2 nodes and the developer sets the deployment replicas to 9, the first 8 pods will schedule perfectly, 1 on each node. The 9th pod will evaluate the cluster, realize there are no unique nodes left, and sit in a pending state forever because the anti-affinity rule strictly forbids it from sharing a node with its siblings.
Spot on. Which brings us to a massive operational challenge. You've got different CPU requests for dev, staging, and prod. You have anti-affinity rules that only make sense in prod where you have 50 nodes, but break staging where you only have 8 nodes. How do you manage all these different YAML configurations without duplicating your Helm charts? I do not want to see 3 separate repositories for the same application.
And you shouldn't. Duplicating charts violates the DRY principle, don't repeat yourself, and leads to configuration drift where a bug fix in staging is forgotten in production. The modern GitOps approach is to maintain a single, universal, environment-agnostic Helm chart for the application core.
How do you handle the environment differences then?
Using hierarchical values files. Inside the Helm chart directory, you maintain a base values.yaml file. This contains the sensible defaults that apply everywhere, the container port, the liveness probe path, the basic labels. Then you create environment-specific override files, valuesdev.yaml, valuesstaging.yaml, and valuesprod.yaml.
Walk me through how the Helm engine processes those files during a deployment.
Helm merges the values files from left to right, with the rightmost file taking precedence. When you execute a deployment to production, the CI system runs helm upgrade -- install myapp./chart-f values.yaml-f valuesprod.yaml. The Helm templating engine loads the base file first into memory. Then it loads the prod file. Any keys that exist in both files are overwritten by the prod settings.
So the valuesprod.yaml doesn't need to contain the whole configuration.
Exactly. It might only be 15 lines long. It only contains the deltas. It overrides the replica count to 50, increases the CPU request to 2 cores, and sets the anti-affinity rules to required. Everything else is inherited dynamically from the base chart.
That is elegant. But human beings running Helm upgrade commands from their laptops is how we got the deletion disaster earlier. How do you automate this?
We implement true GitOps using Argo CD. We install the Argo CD controller inside the EKS cluster. We don't push changes to the cluster anymore, we pull them. We define an Argo CD application custom resource for each environment.
How does that look?
The production application object is configured to watch the main Git repository. We explicitly tell Argo CD to use the Helm plugin, and we pass it the paths to values.yaml and valuesprod.yaml. Argo CD constantly monitors the Git repository. If an engineer merges a pull request changing a memory limit in valuesprod.yaml, Argo CD detects the Git commit, renders the new YAML in memory using the merge values, calculates the diff against the live cluster state, and automatically syncs the changes to production. No human ever runs a deployment command.
We're in the home stretch, candidate. Phase 6. The ghost in the machine. You've set up Argo CD. It works flawlessly. You merge a PR to deploy a new version of the application to production. Argo CD syncs the state. But the new pods immediately fail with an image pullback-off error. The exact same image tag, hosted in AWS Elastic Container Registry, deployed perfectly to staging just 2 hours ago, is not a typo. The registry URL is correct. The image exists. Why is production failing a pull it?
If the tag is correct, the image exists and the network is open, an image pullback-off is almost always masking a 401 unauthorized authentication failure, and in AWS EKS, this points to the 12-hour authentication token ghost.
Elaborate on the token ghost. Why 12 hours?
By design for security purposes, the authentication tokens used to access AWS ECR are not permanent credentials. They are temporary STS tokens. Security token service tokens that strictly expire every 12 hours.
But a Kubernetes node runs for weeks or months at a time. How does it ever pull an image after the first day?
Under the hood, the kubelet uses an integrated ECR credential provider plugin. Before the 12-hour token expires, the kubelet reaches out to the AWS API to request a fresh token, quietly renewing its access in the background. But it requires AWS IAM permissions to do that.
I see.
Yeah, if the IAM-ins instance profile attached to the production worker node is missing the eCure get authorization token permission, maybe the Terraform script for the prod node group had a typo. The initial boot works because of instance metadata, but the background refresh fails silently.
So 12 hours after the production node boots up, it suddenly loses all ability to pull new images.
Exactly. Staging worked because maybe the staging auto-scaling group had just cycled a new node an hour ago, so its token was fresh. The prod nodes were older than 12 hours, their tokens expired, the refresh failed, and the registry rejected the pull request with a 401, manifesting as an image pullback-off in Kubernetes. The fix is to attach the Amazon ADC2 container registry read-only manage policy to the node's IAM role.
Let's talk about background tasks. Question 15. Did the images pull successfully? But the data team just escalated an issue. Our 2 a.m. nightly database aggregation jobs have been failing silently for 3 days. No PagerDuty alerts fired, no crash logs were generated. The Kubernetes cron job object just stopped creating pods entirely. Why did the schedule die?
Silent failures in batch processing are terrifying because your monitoring tools usually look for errors, not the absence of an action. If a cron job stopped creating pods entirely, I immediately check the cron job configuration using kubectl get cronjob-oyam. I am specifically looking at the concurrency policy field.
Break down how concurrency policy becomes a silent killer.
The concurrency policy dictates what Kubernetes should do if it's time to start a new job, but the previous job hasn't finished yet. If the policy is explicitly set to forbid, which is common for data jobs to prevent database table locking, it tells the controller, never run 2 instances of this job at the same time.
That sounds like a safe configuration.
It is, until a job hangs. Let's say the Monday night 2 a.m. job connects to an external vendor's API. The vendor's API goes down, but doesn't close the connection. Your pod just sits there, waiting for a packet that will never arrive. The job doesn't crash, it just hangs in an active state indefinitely.
So it's just stuck.
Right. When Tuesday at 2 a.m. rolls around, the Kubernetes cron job controller wakes up, checks the schedule, and sees it's time to run. But it also checks the current state. It sees the Monday job is still marked as active. Because the concurrency policy is forbid, the controller politely backs off. It silently skips the Tuesday execution.
And Wednesday? And Thursday. It will wait forever without throwing a single error.
It's waiting in line behind a dead guy. How do you permanently architect a defense against this?
2 steps. First, to unblock the queue immediately, I manually delete the zombie Monday pod. The controller will instantly spin up the next job, but for a permanent architectural fix, every single job and cron job template must have an active deadline seconds parameter defined.
How does that help? If I set active deadline seconds to 3600, I am instructing the cluster to automatically terminate the job pod if it runs for longer than 1 hour. It acts as a cluster-level timeout. It kills the hung job, preventing the queue from blocking, and triggers an actual failed event that Alert Manager can catch and send to PagerDuty.
That is how you build resilient automation. Let's look at the logs for that job. Well, wait, we can't. Question 16. To manage logging, we use the classic multi-container pod design. The main application container runs alongside a Fluent sidecar container within the same pod. The application writes logs to a shared volume, and the Fluent sidecar reads them and ships them to Elasticsearch. But the Fluent sidecar keeps getting UBIM killed and restarting. The application is fine, but the log shipper keeps dying, consuming all available memory. How do you troubleshoot and fix a sidecar architecture?
The primary architectural danger of the sidecar pattern is resource contention. Both the application container and the sidecar container exist within the exact same Kubernetes pod, which means they're encapsulated by the exact same overarching Linux for group boundary.
So they share the same memory pool?
Yes. And if you do not explicitly define individual resources limits for each container independently, one greedy container can cannibalize the memory of the other, eventually triggering an OM kill for whichever process the kernel deems less critical.
But why is Fluent getting greedy? It's just a log shipper. It reads text and forwards it over the network.
Because of how log shippers handle network latency, Fluent uses an internal buffering system. It reads the logs from the file system, holds them in RAM, and batches them before sending them over the network to Elasticsearch. If the application suddenly starts spewing a massive volume of stacked traces, say 10,000 lines a second due to a bug or worse, if the Elasticsearch cluster experiences high latency, Fluent can't ship the logs fast enough.
So it buffers them.
It buffers them in memory. The buffer grows. It's like a leaky pipe pouring water into a bucket, but the drain at the bottom is clogged. The bucket keeps filling up until it consumes all the pod's allocated memory, and the kernel drops the hammer on Fluent.
How do you fix the bucket?
First, at the Kubernetes layer, I set strict independent memory limits and requests on the Fluent container spec. I put it in a hard box so it can never threaten the memory of the main application.
That protects the app, but Fluent will just crash faster now.
Exactly, which is why, second, at the application layer, I modify the Fluent configuration file. I set a hard limit on the buffer size, using total limit size. But crucially, I must configure the overflow action parameter. I set it to drop poll chunk.
Oh, wow.
Yeah, this instructs Fluent that if the buffer fills up completely, it should start permanently deleting the oldest logs to make room for the new ones. It sacrifices the data to ensure the process survives and the pipeline doesn't completely collapse. Drop the logs to save the ship.
A tough pill to swallow, but a necessary engineering trade-off. Welcome to Phase 7, Candidate, the final boss. Question 17. We manage a high-frequency trading application. The market is open. We need to toggle a critical feature flag that controls a trading algorithm. That flag is stored in a Kubernetes ConfigMap. But here's the catch. Every single second of downtime during market hours costs the firm millions of dollars. You absolutely cannot restart the pod. How do you hot reload that ConfigMap configuration into the running application?
The feasibility of a hot reload without a restart depends 100% on how the deployment YAML was originally architected to consume that config map. There are two primary ways to inject a config map as environment variables or as a mounted volume.
Assume the developer mounted the config map as environment variables using n-from.
Then it is physically impossible. When a Linux process boots up, the environment variables are baked into the process's memory space. The kernel does not allow external entities to arbitrarily inject new environment variables into a running process without a full restart. If it's configured as environment variables, a pod restart is a hard requirement.
Okay, assume the senior architect caught that during review. The config map is mounted as a volume.
That changes everything. When a config map is mounted as a volume, Kubernetes creates a physical file, let's say /etc/config/featureflags.yaml inside the container's file system. When you run kubectl, edit config map, and change the feature flag, the kubelet agent running on the node detects the change. Every 60 to 90 seconds, the kubelet performs async. It reaches into the pod's file system and updates the symlinks point that file, updating the contents of the file on disk without touching the running container process.
So the file updates. Does the application just magically know the configuration changed?
No, and that is the fatal assumption many engineers make. The file on disk changed, but the application likely loaded that file into its RAM when it booted up 6 days ago. It is still operating on the old rules. Kubernetes handles the file system, but the application code itself must take responsibility for hot reloading. The developers must write a file watcher loop using something like ftest.watch in Node.js or Viper in Go that actively monitors that file path for changes. When it detects a file modification, the application code must autonomously reread the file into memory and update its internal state.
And if the developers didn't write a file watcher, what tool do we use then?
If the app is dumb, the industry standard is to use a tool like Reloader by Stagator. It's a controller that watches config maps, and when it sees a change, it automatically triggers a graceful rolling restart of the associated deployment. But since you stipulated absolutely no restarts for this trading app, Reloader is off the table. The application code must be rewritten to handle its own hot reloads via file watchers.
Perfect delineation of responsibilities. Let's raise the stakes to the absolute maximum. Disaster recovery. Question 18. Let's assume the nightmare scenario. A disgruntled employee or a severely botched CI/CD automation script just ran Terraform destroy -- auto approve against our production AWS account.
Oh my God.
The VPC is gone, the subnets are gone, the EKS control plane is deleted, the worker nodes are terminated, you have zero infrastructure. Start the clock. How do you recover the company?
This is the extinction level event. A true disaster recovery strategy relies on separating the recovery into two distinct streams: infrastructure reconstruction and state restoration.
Stream 1. The infrastructure is ashes. Go.
I immediately lock down the compromised CI/CD pipelines to ensure the destroy command isn't fired again. Then I pivot to our centralized Git repository where our infrastructure as code lives. Because we strictly use Terraform for everything, I can execute a Terraform apply. The Terraform engine will read the declarative state and systematically begin calling the AWS APIs to rebuild reality. It will recreate the virtual private cloud, stamp out the public and private subnets, rebuild the IAM roles, and provision a completely fresh, empty EKS cluster. The beauty of Terraform is that this process is largely mechanical and takes roughly 20 to 30 minutes.
Okay, 30 minutes later, the cluster is back online, but it is completely empty. There are no namespaces, no deployments, no pods, and critically, none of the databases have their data attached. How do you restore the soul of the cluster?
This is where Velero saves the company. Velero is the gold standard for Kubernetes disaster recovery. Prior to the disaster, Velero was running in the cluster, taking nightly snapshots of all Kubernetes objects, the YAML definitions inside, etc., and saving them to an offsite Amazon S3 bucket. Crucially, it was also integrating with the AWS CSI driver to take physical snapshots of the underlying EBS volumes and storing those in AWS.
How do you trigger the resurrection?
I installed the Valero CLI on my local machine, pointed at the fresh EKS cluster, and pointed to the offsite S3 bucket containing the backups. I run Valero restore, create -- from backup nightly prod backup.
Walk me through what Valero actually does under the hood when you hit enter.
Valero connects to the API server and starts pouring the state back in. First, it recreates all the namespaces, RBAC roles, and service accounts. Then it starts redeploying the persistent volume claims. Here is the magic. When Valero deploys a PVC, it tells the AWS CSI driver to dynamically provision a brand new EBS volume, but it explicitly tells AWS to hydrate that new volume using the snapshot ID from the backup.
That's incredible.
It is. AWS spins up the drive with all the database files perfectly intact. Finally, Valero redeploys the deployments and services. The pods boot up, attached to the freshly restored EBS volumes, and the databases come back online with their data. Assuming the EBS hydration is fast, the total recovery time objective is roughly 45 to 60 minutes.
You resurrected the cluster from ashes. Highly impressive. But now that we are back online, we have a governance problem to solve. Question 19. 4 different development teams are sharing this resurrected cluster to save costs. Team A is reckless. They run massive machine learning data crunching workloads. They constantly deploy pods with 0 resource limits configured. When their jobs kick off, they consume 100% of the CPU on the worker nodes, completely starving teams B, C, and D, causing their latency to spike and their pods to crash. How do you build an automated multi-tenancy shield to control Team A?
In a multi-tenant cluster, you cannot rely on developers to police themselves. The platform must enforce boundaries at the API level. I will apply 3 distinct layers of armor. Layer 1 is a limit range object.
What does a limit range do?
A limit range is a policy applied directly to Team A's specific namespace. It acts as an automatic injection mechanism. If a developer from Team A deploys a pod and forgets, or intentionally omits, the CPU and memory requests and limits in their YAML, the limit range intercepts the API call and automatically injects sensible defaults, say 500 millicores of CPU and 1 GD of memory into the pod spec before it is saved to the database. It forces every single pod into a defined box. No pod can be limitless.
Okay, every pod is in a box. But what if Team A writes a script to deploy 1,000 perfectly boxed pods? 1,000 small pods will still consume the entire cluster's capacity.
That is the vulnerability of a limit range. It only cares about individual pods. To solve the aggregate problem, we apply layer 2, a resource quota. A resource quota puts a hard, unyielding cap on the total resources a namespace can consume collectively. I configure a quota on Team A's namespace that says they can only request a maximum of 16 CPU cores total across all their running pods. If they have 16 pods running and they try to schedule a 17th, the Kubernetes API server flat out rejects the deployment with a quota exceeded error. They are mathematically fenced into their corner of the cluster.
Excellent. You fenced them in.
Yeah.
But let's look at layer 3. Let's say the entire cluster is completely full. Every node is at 90% capacity. Teams A, B, and C are all playing nicely within their quotas. But suddenly, the production payment service, which belongs to Team D, experiences a massive Black Friday traffic spike. The HPA tries to scale up the payment pods to handle the load, but the cluster's full. The new payment pods are stuck in pending. How do you ensure the critical workloads get room?
We implement layer 3, priority class. Kubernetes scheduling shouldn't be first come, first served. It should be survival of the most important. We create a priority class object named critical production and assign it a massive priority integer value, say 1 Nelson. We assign a baseline priority of 1,000 to the dev and batch processing workloads. We configure the payment deployment to use the critical production class.
How does the scheduler handle the conflict?
When the cluster is full and a new payment pod needs to schedule, the kube scheduler sees the high priority value. It looks at the nodes, finds the lower priority dev or batch pods, and it actively assassinates them. It triggers a preemption event, gracefully evicting the dev pods, freeing up the CPU and memory, and immediately schedules the critical payment pod in their place. The less critical teams experience temporary disruption, but the core revenue-generating service stays online.
Brutal, ruthless, and absolutely necessary for enterprise reliability. All right, candidate. Final question, question 20. We've talked through every failure mode imaginable. I am tired of reacting to pages at 2 a.m. I want you to build me a proactive, production-grade monitoring and observability stack from scratch so we never have to guess about any of these metrics or bottlenecks again. Architect it for me.
A modern observability stack needs to gather metrics, visualize them, and route alerts intelligently. I'm deploying the Prometheus stack via Helm. It is the undisputed industry standard. It gives us Prometheus as the time series database for scraping and storing metrics. It gives us Grafana for building rich visual dashboards. And it deploys Alert Manager for handling the alarm routing.
It's a great stack, but tools are only as good as the telemetry they gather. What specifically are you configuring Prometheus to monitor? Don't give me a generic everything. Give me the framework.
I strictly adhere to Google's SRE framework, the 4 golden signals.
Walk me through them.
First is latency. I configure Prometheus to track the P99 response times per microservice via the Ingress controller metrics. I don't care about the average, I care about the slowest 1%. I want an alert fired if the P99 latency breaches 2 seconds.
And the second?
Second is traffic, the total number of HTTP requests per second. I want anomaly detection alerts on massive sudden spikes, which indicates a DDoS attack, or a sudden drop to absolute zero, which means the load balancer or DNS just broke. Third is errors. I track the rate of 5xx HTTP errors compared to 2xx successes. If the error rate breaches 1% of total traffic for more than 5 sustained minutes, wake the team up.
And the final signal?
Fourth is saturation. This is the physical hardware limit: CPU, memory, disk I/O, and network bandwidth. I configure alerts to trigger when we hit 80% utilization, not 100%. If you wait for 100%, the system is already dead. Alerting at 80% gives the engineering team time to react, debug, and scale capacity before the users ever notice degradation.
You've got the metrics. But if you alert on every little fluctuation, the engineering team is going to suffer from severe alert fatigue. They will start ignoring the alarms, and a real outage will slip through. How do you handle alert routing?
Through aggressive severity tagging and alert manager routing rules. Not every anomaly is a pager waking event. I configure routing logic based on the impact. Critical, user-facing alerts like a deployment entering a crash loop, etcd high latency, or the 5xx error rate spiking are tagged as severity critical. Alert Manager routes those directly to PagerDuty to bypass Do Not Disturb on the on-call engineer's phone at 3 a.m.
What about the non-critical stuff?
Warnings like a single pod restarting once or a node hitting 75% disk usage are tagged as severity warning. Those are silently routed via webhook to a dedicated Slack channel. The team reviews the Slack channel the next morning over coffee. Protect the team's sleep, but protect the cluster's health.
Wow. You know what? You are hired. That is exactly how you pass a senior DevOps architecture interview at the absolute highest level.
Thank you. I appreciate it. That was a really intense gauntlet to run through.
It was, and honestly, stepping back and looking at the entire architecture we just mapped out, it is staggering how deeply interconnected these systems are. Every single scenario highlighted a hidden web of dependencies. A simple missing CPU request and a YAML file completely paralyzes the autoscaling math.
Yeah, or an invisible 12-hour IAM token timeout breaks an automated deployment pipeline. A missing finalizer traps a physical hard drive in the cloud. It's fascinating, but it's incredibly fragile if you don't understand the mechanisms underneath.
It's an ecosystem. If you change the temperature in one room, the humidity changes in another. That's why having those strict layers of governance, the limit ranges, the resource quotas, the RBAC, the priority classes, isn't just corporate bureaucracy. It's the only way to keep the ecosystem from collapsing in on itself when humans inevitably make mistakes.
Exactly.
To you, the listener, what stood out to you the most during this deep dive? Was it the silent, terrifying failure of those cron jobs quietly waiting their turn forever? Or maybe the realization that base 64 is absolutely not encryption and you need to go audit your Kubernetes secrets right now.
I really hope someone out there is checking their deployment YAML to add pre-stop hooks so their customers stop getting 503 errors every time they push new code.
Definitely. We covered an immense amount of ground today, from Linux kernel mechanisms like OM killers and ARC groups to AWS network exhaustion to the intricate dance of zero downtime routing. But stepping back from the technical weeds, it raises a really important philosophical question for you to mull over. We've built these incredibly sophisticated, self-healing, automated orchestration systems. But at what point does the sheer complexity of managing the automation, managing the operators, the service meshes, the IAM federations, the layers of YAML, at what point does that complexity become a bigger operational risk than the actual application code it was designed to run? Are we building resilient infrastructure, or are we just building much more complicated failure modes? Something to think about the next time you run Kubenetes Apply. Until next time, keep diving deep.